And so now I'd like to get started with this session, Advanced AI Reasoning from Game Mastery to Complex Problem Solving. I'd like to introduce Vardika Singh, our moderator. She leads strategic technical partner engagements at NVIDIA. Vardika possesses in-depth understanding of mechanics of machine learning and deep learning over scale, architectures, and hardware. She is passionate about designing and architecting teams and solutions around data, leveraging a wide array of frameworks, technologies, and platforms.
Thanks, Georgine. Can you guys hear me? OK, thanks. So welcome to GTC. My name is Varika Singh, and it's my pleasure to host today's panel, Advanced AI Reasoning from Games to Complex Reasoning. I wanted to take a couple of minutes to set context for today's panel. Today's AI is in a pivotal moment. We have algorithmic breakthroughs converging and enabled by ever-expanding computational capabilities. And in today's conversation, we have two leading figures whose work exemplifies this convergence. So we have Noam Brown from OpenAI, whose work led to several breakthroughs in our understanding of how AI can excel in strategic complex reasoning and games. And we have Brian Catanzaro, who is VP of Applied Deep Learning Research at NVIDIA, and has been at forefront in architecting scalable training and deployment systems at industrial scale. So having said that, maybe we can take a few minutes to kick off by placing your work in context of AI reasoning. So Noam, would you like to get started?
Sure. So I started in the AI field around 2012. I started my PhD at Carnegie Mellon. Worked on AI for games, initially AI for poker. And at the time, there had been a lot of progress in chess, similar perfect information games. There had been continuing progress in Go, but nobody really knew how to extend those techniques to poker, which is an imperfect information game. And so my PhD research was on, OK, well, how do we enable superhuman poker AIs? And more generally, how do we enable superhuman AI in imperfect information games? So that was about 6 years of my PhD. In 2017, we developed the first superhuman poker AI. We followed this up in 2019 with the first superhuman multiplayer poker AI. So 2017 was two-player, 2019 was multiplayer. And after that, I went to, in 2018, I went to Meta, where I also worked on the multiplayer poker AI. I did it there, actually. And then switched my focus to, among other things, trying to extend this to the natural language game of diplomacy. And while there, my colleagues and I developed the first human-level diplomacy AI. And all these techniques, I noticed, was using reasoning. So a big focus was on, OK, how do we enable the AI to think for longer when it's making a decision to arrive at a better outcome? And the thing I noticed through all of this is that, OK, well, the techniques that we used in poker are very different from what's used in chess, and the techniques that we used in diplomacy are very different from what's used in chess and poker. Can we develop a very general way of doing reasoning, ideally in something as broad as language? And so that motivated me to then come to OpenAI, where I worked with a lot of other amazing colleagues to develop the O1 system.
Brian?
Great. Really impressive work. I started, I guess, in working on systems for AI back when I was a grad student. And I published my first paper on that in 2008 at ICML. I showed up and said, hey, here's how to train some models on the GPU. And back then, people said, why are you here? That was the response that I got. At the time, I think it wasn't as obvious how important compute would be to the development of artificial intelligence. But I believed that there was a big opportunity to push artificial intelligence forward and by pushing on the systems for compute. And so I joined NVIDIA full-time in 2011. And my work back then led to the creation of cuDNN, which was NVIDIA's first library for AI on the GPU. And since then, I've had the fortune to be involved in a lot of other projects, including DLSS, which uses machine learning to speed up the graphics rendering process. And these days, we're about 8 to 10x more efficient in graphics rendering because of our real-time application of AI, which I'm really excited about, especially now that AI is entering virtual worlds and interacting in new ways. I think that's really important. And then also, we've been working on systems and for language for quite a few years. We built a system called Megatron, which I think has helped push the industry forward, helped scale large language model training, and I'm really excited about the possibilities to take all of this work in systems for AI to the next level to support reasoning.
Thank you. Impressive work, both of you. So let's start with the games part. So you mentioned, I see a clear demarcation, or somewhat of a demarcation between Libratus and Pluribus, and then Cicero. So you mentioned that there was a cohesion between three, which led to O1, the reasoning in O1. Could you describe which techniques are you really thinking about in those two?
Yeah, I think what's really interesting about my prior work in poker is that the techniques. Okay, so I'd say a lot of the early work on poker actually didn't focus that much on reasoning.
Reasoning, yeah.
Yeah, a lot of it was kind of like pre-training. You know, you would spend a lot of time training these models, maybe 2 or 3 months on a large system. We weren't using GPUs; we were actually using CPUs back then. But when it came time to actually play, the AI would act very quickly, maybe 10, 100 milliseconds. It's just a lookup table.
Right.
And there had been some work investigating how do we enable more inference compute for these systems, but it wasn't really a priority in the research. And part of it, there were various reasons. One is that it was very just difficult to do. I mean, it's pretty well known now how you do it in chess. The answer was alpha beta pruning, and then in Go the answer was Monte Carlo tree search. But neither of those techniques worked in poker, and so nobody really had a very good answer for how to do it well in poker. There were also a lot of other reasons. Poker is a very high variance game. If anybody's played poker, you know that you could be a terrible poker player but still win because you get lucky. And even with pro poker players, they have to play. They could spend a whole year playing poker and still be down money because they just had a bad year. And so that poses a problem if suddenly you go from spending 10 milliseconds per hand to 20 seconds per hand, because if you have to play a million hands of poker to tell if one AI is better than the other, you don't want to spend that time. So there were various reasons why this research direction was neglected, and the biggest reason is that people just didn't realize how big of a difference it would make. And so I noticed over the course of my research that, okay, there's something missing. Humans spend a lot of time thinking before they act in a tough situation. Maybe this would be very useful. And then when I investigated this and saw how much of a difference it made, it became very clear to me, oh, this needs to be scaled up.
Okay.
Now, the techniques that we ended up using are very different from what's been used in chess and Go and other techniques. And so I think that's, for me, the real takeaway, that there wasn't just one universal system.
Right. So there was a shift from system 1 to system 2.
Oh, yes, yeah.
Yeah. Okay. So that's like Pluribus. It's while you're playing, you respond instantly.
So that was Libratus. That was the 2017 AI was called Libratus, and that was in my opinion, the big breakthrough.
Yeah.
And then in 2019 we had Pluribus, which I think took this even further. Yeah. And the details of the difference are not that important, but the main thing is that it was a lot cheaper. We developed an even better way of scaling inference compute that made it even cheaper. Yeah. And Pluribus, in 2019, it cost less than $150 on cloud computing to train. Yeah. And I think what that result really shows is that this wasn't just Moore's law. It wasn't just, we were scaling up compute. We actually had a different paradigm that leveraged a lot more compute at inference. And because of that, we were able to do this. And it could have been done 20 years earlier if people knew to take this approach and knew the algorithms to use.
So you said, I heard you say somewhere, or read somewhere, so you said $150 for training it.
Yeah.
So while you're playing the game, it was somewhat like 100K versus 50K?
It was using, for Pluribus, it was using 28 CPU cores at inference time.
Okay.
For about 20 seconds per hand. And that's pretty cheap, but if you compare it to what was being used before, which is just one CPU for 10 milliseconds or something, it's a big scale up in terms of inference compute.
That's impressive. So let's move on to your work on diplomacy and Cicero, where you incorporated a language component for the dialogues and negotiation and
well, first of all, maybe, Noam, you could explain the game of diplomacy. Maybe not everybody's played it before.
Yeah. Hoping that everybody knows about poker, but for diplomacy, okay, so diplomacy is a 7-player game. It involves natural language communication. In fact, the real complexity of the game is about negotiating with the other players. The rules of the game, the actual mechanics, are very simple. The complexity comes from interacting with other people. And so after we had...
And I want to say, when I was a grad student, my friends and I would play diplomacy, and it could take a week or a month to play a game of it, because it really is all about the interaction between the people.
Yeah, it's also a very brutal game. You work with somebody for 5 hours, you think you have a good alliance going, and then they, backstab you, and yeah, it's not an easy game to play. But I really admire the game because it's so different from like all these other strategy games that are so focused on the mechanics. The complexity of diplomacy is really about the people. And so after we had this success in poker, and then at the same time there was also success from DeepMind on StarCraft and OpenAI on Dota 2, and we were thinking about, okay, what should we focus on next? And around that time also, we saw this breakthrough happening in language models. So GPT-2 had just come out in 2019, and we thought, okay, we would always... my colleagues and I had discussed diplomacy. I actually thought it would have been crazy to work on diplomacy. I was like, this is way too hard. But my colleague Adam Lear, convinced me that actually, why not? You might as well aim for something big. And we had already had a big success with poker, and so we were thinking like, how could we actually top that? We might as well aim for something that has like it's high risk, high reward. But if we succeed, it'll be really cool.
So just to put a little more framing around this, I think in order to be good at diplomacy, not only do you have to be really good at reasoning and strategic thinking, but you also have to be persuasive. You have to build alliances, and then you have to abandon them at the right time. So this is, I think, a much more difficult task than poker or chess, where the rules are much more harder and mechanical. This is much squishier and much more human.
Yeah.
So that's where I was coming to, that compared to your previous work on those poker-based AIs coming to Cicero, and that was at Meta, right? That was not at CMU.
Yeah, Cicero's at Meta.
Yeah.
Yes.
So that included incorporating something going beyond what you had done before for the AI poker-based AIs.
Yeah, there's, I guess, 2 dimensions that are of complexity for diplomacy. One is that we're going from a 2-player game, a 2-player zero-sum game, to a game that involves multiple players. And there's a whole other session we could have on like the complexity of going from 2-player zero-sum to something that involves real humans and understanding humans. And then there's also a dimension that, okay, now we're in natural language, and what does it mean to reason in such a broad action space? Chess is you have maybe 20 reasonable actions you could take at any given moment. Poker, you got like fold, call, raise, and then obviously there's like questions around how do you balance those actions, but it's still like a relatively constrained space. And then in diplomacy, what is your action space? Your action space is all the things that you could say to another person, and that complexity just takes the reasoning to a different level.
Right. I forgot to ask one question before we jump to Cicero. You mentioned the significant reduction in compute. I think that will set the stage for later on between librettos and pluribus. What made that possible? Mostly algorithmic, right?
From librettos to pluribus?
Yes.
Yeah. We went from the 2-player AI to the 6-player AI, and the cost went down to $150 for training. It was algorithmic improvements.
Yes. So variants of CFR.
It was really the fact that we developed better reasoning techniques that enabled us to then spend less effort on pre-training.
Okay.
And shift more the compute burden to inference.
So when you moved to Cicero, like how did that compute change requirement? So was it a combination of what you were doing on CPUs with poker-based AIs and combination of GPUs?
No, at that point we had moved to, once you're dealing with natural language negotiation, you have to move to neural nets, to language models, and so the compute burden shifted to GPUs.
Right. So if I can pivot to you, Brian. So traditional deep learning has all been matmul heavy. So GPUs work very well for that. And since initial work from Noam and his teammates and his advisors, the work on the poker-based AIs as well as the reasoning has multiplied manifold. So how are you thinking about it when you are designing or doing the research internally at NVIDIA?
Well, the work that we do at NVIDIA is really about trying to understand the world's most important computations and then optimize them end to end. So obviously we build the GPU and then we build the networking, but we build compilers, libraries, frameworks, and we work on algorithms and applications as well. And the purpose of this work of accelerated computing is to make it possible to do something that we couldn't do before. I think Jensen was saying yesterday in his keynote that it was the highest compliment he ever got, that a scientist said, "Thanks to you, I can actually do my life's work in my lifetime."
Yeah.
And so that's our goal at NVIDIA. And we have this belief that the only way to provide the kind of acceleration that really changes the field, that allows breakthroughs like the ones Noam's talking about, is to think about the problem end to end and look for opportunities to accelerate it at every single level of the stack. And so that's what we do. Now, you said something interesting about this work is really MATML heavy, matrix multiply heavy, and that's true. One of the things that I believe is that the evolution of algorithms for AI and systems for AI happens together. The systems for AI have been very important to the development of AI. The algorithms obviously are very important as well, and they tend to, the successful ones tend to evolve together. It's interesting if you go back to 2012 when Alex Krizhevsky and Ilya Sutskever published the ImageNet paper. If you read that paper, which totally redefined the entire field of computer vision, it was primarily a systems paper. It was primarily thinking about how do we train a bigger model in a more efficient way, and so that led to a lot. That systems investment led to a lot of algorithmic breakthroughs that completely redefined the entire field of computer vision. And then there's sort of a virtuous cycle that happens as we iterate. And one of the reasons I believe that the field of AI is so dominated by matrix multiplication is because that's the most efficient way to build a computer that can do a lot of work. The properties of matrix multiplication fit well onto the technologies we have for building systems, for distributing work across the data centers, for building models where we can really just put a lot of compute into the model. And I think that's important. I think now it's clearly not trivial to turn a matrix multiply into intelligence, right? It's taken us as a community decades to figure out how to get to where we are today. But I think it's important to realize that these things, the systems and the algorithms, are connected and they evolve together. And it's been true throughout my entire career that they both need each other, and that the more compute we can put into AI, the better the results and the smarter the algorithms get, which then enable the next round of innovation.
I think that's 100% correct. That there's really a close connection between the algorithms and the compute, and a lot of what goes into designing good algorithms is developing a technique that can leverage the compute most effectively and scale it up most effectively. Like when we're thinking about algorithms, we're thinking about what's the ceiling to this? What happens if we were to scale it up by 1000x? What can it not do? And that was the motivation for certainly a lot of my work.
So a lot of your early work was based out of academia. And I'm seeing a lot of papers and talking to a lot of researchers nowadays, and most of the publication falls just short of what could be exciting, and that's primarily due to lack of compute. But regardless, you did have access to a pretty large supercomputer when you did your initial work. And how much was that a factor? Because your trajectory has been very seamless and consistent since your academia, then transition to Meta, then transition to OpenAI.
It's true that as far as grad student standards go, I had access to a lot of compute for a grad student. We're talking thousands of CPUs, which today, again, is still not that much, but for a grad student back then, it was a big deal. And I do think, in some ways, that ended up being a very, very big factor. I don't think we could have gotten to superhuman performance in poker without those resources. I mean, I said, in 2019, we developed this bot that could be trained for under $150 and ran on 28 CPU cores. And sure, you get to that point, and the last training is very cheap and the inference is relatively cheap, but all the research that goes into figuring out this is the right paradigm, that ends up being very expensive. The fact that you can compare these reasoning techniques and say, oh, you're getting the same performance as if you were to scale up inference by 1,000x and run on 2,000 CPU cores for 3 months. The fact that you can do that comparison requires a lot of resources. And so I think it's a real challenge now. I talk to a lot of grad students that are, they're asking me, like, how can we do impactful research in an era of like even larger scale compute? And it's a tough question to answer. Certainly, it's a much easier, it's certainly a lot easier to do this kind of like frontier capabilities research in frontier lab in these like places like OpenAI. There is still impactful research that can be done in academia. I think exploring radically new paradigms. Frequently, that doesn't require a ton of compute.
Yeah.
But to prove it out at scale certainly requires a lot of compute. But there is an opportunity for collaboration between the frontier labs. I mean, certainly the frontier labs are looking at academic publications and thinking carefully about, okay, does this make a compelling argument that if this were scaled up further, it would be very effective? And if there is that compelling argument in the paper, we will investigate that in these labs. There's also room for things like evals, benchmarks. The state of benchmarks in AI is really bad, and that doesn't require a lot of compute to do.
Yeah, that does require some investment, though, in terms of designing it and putting it together.
It requires a lot of work and a lot of effort, but the compute burden is relatively low.
Yeah.
Well, I think there's also a difference in the way that people go about their work for necessary reasons. So frontier labs can afford to really invest in a thing and make it really big. Like, if you look at the GPT-4 paper, for example, how many authors are on that paper, right? Academics have a need to publish, so that people can graduate. Right?
Fast and frequently.
People need to get a PhD thesis, and so they need to own a piece of the work. And the reason that I'm telling you this is because I actually believe that the first thing that AI is eating is AI research. Because the forces that push us to collaborate to build bigger things that have more people involved and we can really make big bets and make investments, that makes it very difficult for a kind of research model where we have a lot of tiny projects that are each trying to be state of the art in some way. And I think this is pushing the field towards a model where there's a lot of really interesting and important work that's coming out of academia, but it has to be done at a smaller scale. And then the process of integrating that into frontier models that that actually get deployed, the kinds like that you build at OpenAI, I think that has to be done kind of as a second step. Just because the kinds of investment we're talking about to build these models is so large that I think it really is changing the way we do the research.
Yeah. So I do want to move to the next topic, but I want to touch, so you lead the applied deep learning research team at NVIDIA. How does this impact you, if at all, like converging the research and then taking it back to
this is my life every day. I mean, this is what I do every day, is to try to convince researchers to work together. I think on a sort of at a high level, everybody kind of understands that. Like, everybody kind of understands, like, yes, we'll have a much more impactful result if we're able to figure out how to work together. But also, researchers are independent. That's how they were trained. That's how they were brought up. And so trying to show people that, their careers are going to do better if they figure out how to collaborate on something big. That's a lot of mind shift, I think, for people, and something that I do spend a lot of time on. Now, having said that, like, in smaller scale investigations into like new paradigms for things that can be really innovative and inventive are absolutely still required. I have absolutely no doubt that AI is going to change radically in the next 10 years because of some amazing ideas that that people are going to find, and I'm really excited to see that, and so I'm not trying to discourage people from doing that, but I think the purpose of it has to be kind of put into context, and I think that is a shift for a lot of people.
Yep. It's a topic that warrants further discussion. Moving back to your excitement on diplomacy and Cicero, going back to that work. So earlier we were talking and you mentioned this O1 and then there's the prior work. So there's a little bit of a difference in terms of what the end goal is. But like folks have a lot of excitement about something like diplomacy, and you got that working in a game environment kind of scenario. Do you see any transition to real world situations like negotiations or multi-government conversations, things like that?
I think for the diplomacy work, the Cicero work on the game of diplomacy, we learned a lot from that work, and I think the community learned a lot from that work. I think we learned a lot about what does it mean to develop AIs for multi-agent environments. What does it mean to reason in a very flexible, open-ended environments? The techniques that were used for diplomacy were, to some extent, somewhat specific to diplomacy. And so, if you're asking, like, could Cicero be used in a real-world negotiation?
Yeah.
Out of the box, no.
Out of the box, no. Yeah.
No.
Yeah.
But that wasn't really the purpose. The purpose was that we're gonna, like, there's this domain, the natural language game of diplomacy, that if you take all of the existing techniques that take AlphaZero, you take Pluribus, and you try to apply it to this game, it just doesn't work. So something is missing. And then to explore that domain and figure out what is this thing that's missing, you learn a lot from that process.
Okay.
And the academic community learns a lot from that process. And one of the things that I took away from it is that you need to develop the reasoning techniques that were developed were too narrow. One of the beautiful things about deep learning is that it's an extremely flexible paradigm. You throw a transformer at, like, all these different domains, and it just kind of, like, works out of the box. And the fact that we had to develop these very domain-specific reasoning techniques for all these different settings, for poker, for chess, for Go, for diplomacy, it just slowed down the development process. Like, yes, you could do it. You developed a reasoning technique that works in diplomacy. We got very strong performance, but that took, like, years to develop that. And if we then wanted to go to something like actual real-world negotiation, it would take another years to develop a technique that works for that.
Yeah.
And so my takeaway from the work was that we needed to develop a reasoning approach that was as broad and as flexible as deep learning had been for system one thinking.
Okay. So, like, the question for both of you, right? So eventually, I assume we get there where this is a true multi-agentic environment where a negotiation is happening. And in that situation, like, the computation, the advances in compute, the advances in algorithm have to go hand in hand together. How do you see that playing out, Brian?
Well, I thought Jensen did a pretty good job of laying this out in his keynote yesterday. He was talking about different kinds of scaling for different kinds of tasks, and I think we're definitely seeing that reasoning as a compute problem is just enormous, because when we're training these models and when they're learning how to reason, they need to practice, right? And they need to learn, and they need to try it out, get feedback, try again. And so this is an opportunity to convert compute or inference from these models into intelligence in a way that we haven't done before. And so that's the way that I'm thinking about it. Now, this has enormous implications for the kinds of systems that we're going to be building and the kind of software that we're going to be running to do this. It is quite different than the pre-training heavy model where the vast majority of the work just went into training a model, a bigger and bigger model on a bigger and bigger data set. I think pre-training is still very important because I think of pre-training as kind of a foundation, upon which we can build reasoning. The better the foundation, the better the reasoning. And so we're still seeing like improvements that are faster than Moore's law in terms of like how much quicker can we train a model, how much more intelligence can a model have for the same amount of compute. We're seeing faster than Moore's law rates of improvements because of all the work that's going into the base model itself. But then, the amount of compute that we're devoting into post-training and reasoning compute is growing really fast. And so that's really exciting for us. It's exciting for NVIDIA to think about, the implications of that on networking and on low precision arithmetic and sparsity, and how are we going to architect the next generation of systems for reasoning. But I would say that that's our number one priority. Like if you just looked at the way that it was talked about in the keynote yesterday, like we feel like this is just such an enormous opportunity for the world, and we're so excited to help push it forward.
Yeah.
I think it's 100% correct. I think we're in a really exciting moment now, where now we have these reasoning models. Like I think, starting with O1 that can reason in a very broad way, and it's like a new paradigm, in my opinion. In the same way that the arrival of AlexNet led to like a huge investment in inference, not in like
Training.
in like hardware for GPUs and everything. I think we're at a point now where we have reasoning models that can do the system 2 thinking, not just the system 1. And there's a lot of room to scale that, and there's a lot of room to like develop hardware that is focused on that now. And that's not to say that, I agree also that pre-training is not dead. I talk to people that have tried to do these, develop reasoning techniques for small scale LLMs, and it just doesn't work. Like you try to do something like O1 on GPT-2, it's not going to get off the ground. So they are complementary. They do go hand in hand, and I think that we're going to see progress on both.
Yeah, I think that maybe the goal is shifted. Like the goal of pre-training, at least when I was working on pre-training in the past, my goal was just try to get a model that
Converges.
Well, of course we want it to converge, but try to make the model as big as possible. Try to train it on the biggest data set as possible, and then the model's going to be used in more of this system 1 kind of way, where you just you give it a question, it's going to make an answer, right? And so in that, when you're thinking about the balance of how do you build the system and then how do you use the system, it's like most of the compute is going into building the system, and then the using the system is fairly straightforward. With the advent of these reasoning techniques, now we have a much more complex training process because there's a lot of inference that's now part of the training process. And so the software and the hardware for doing large amounts of inference during the reasoning post-training process is completely different than what we used for pre-training. And there's enormous opportunities to accelerate that. And so I'm super excited about that. And then also when the model's deployed, it is now the case that, in my opinion, that inference cost is directly connected to intelligence, because if you make a model much cheaper to infer, what that means is that it can think for longer, and then it's going to solve the problem much better. And that wasn't the case in the past, right? Like in the prior way of thinking about it, you kind of want to make the model as heavy as possible because that's going to make it the smartest as possible. Now we want to make the model kind of at an optimal point, like what's the absolute maximum intelligence that we can cram in per inference cost, and then that is ultimately going to be the smartest model. So that's a completely different problem from an accelerated computing perspective.
I think that's a really good point that a lot of people maybe miss, that the notion of model intelligence, performance on a benchmark as a single number doesn't really even make sense anymore. You have to think of it as intelligence per dollar or per token or something like that. If a model can think for a very long time, it's going to do better on all these benchmarks. And so you really have to think of it as a curve of intelligence versus cost curve. And the ceiling can be very large, can be very high. if you're willing to spend a lot. And that's kind of the future that we're headed towards, I think.
And we will be willing to spend a lot. I'm fairly certain, because if you look even at our most expensive models, they're amazingly much cheaper than I am. They emit less carbon than I do. And that means that we're going to be able to find ways to use them to solve many more problems than we can solve today. And I think we are going to be, as a community, figuring out ways of having really sort of involved inference procedures solve really important problems. And I think that's going to change the way AI is applied.
Yeah. I think when people think of they look at these reasoning models and they think, oh, this thing is so expensive. And well, compared to what? If you're comparing it to GPT-4o, then sure, it's very expensive. But if you compare it to a human trying to do the same task, then it's dirt cheap. And that comparison to a human matters, especially as the intelligence grows. Once you have these models surpassing top humans in certain domains, you think about how much the top human in the world would be paid to do a task. They command a big premium for that expertise. And when you have the models now having that expertise, and they're like a fraction of the cost of a human, there's a lot of value in that.
So going back to the topic of the panel, you learned certain things from the interplay of games and the humans. So your shift from librators to pluribus, that observed people are taking longer time to think before they're answering. Is that something that you're going to revisit? Because there's some aspects of human nature, like adaptability and all, are not actually captured yet. Is that an open field, or is there some other Noam Brown working on it?
I think if you look at the paradigm of AI that exists today, we don't have all the research questions figured out. There's still open research questions that need to be investigated and solved in order to unlock, I would say, across the board, like super intelligence. I think if you look at the pace of progress over the past 15 years, especially the past 5 years, it's, I think, exceeded everybody's expectations. And I think it's I think there's a lot of AI critics out there that point to certain things and say well, the models can't do this, they can't do that. People have been saying this for 10 years now. And
for longer.
For a lot longer, yes. But it's really about the trajectory that you have to look at. Yes, there are things that the models can't do today, but there are people working on it. There's very good reasons, in my opinion, to be optimistic that progress will be made. And so you have to think about where it's going to be in 1 year, in 2 years. And I think it's going to be very impressive. I mean, I think even if there's no further research progress, the models that we have today are already going to be transformative.
Okay, so we are at the end of the time. So one question for both of you. What does the ideal world look for you in a couple of years with the most advanced AI reasoning possible?
Is it an ideal world?
Yes.
Do you want to start?
Assuming that all of this research comes to pass and people figure out how to apply.
And let's not talk about legality of it yet. Yeah.
Well, I think AI is going to be legal because we need it. I think the world needs AI. When I look around, there's just so much need in this world for intelligence. There's so many problems that we don't know how to solve. So many opportunities for us to find ways to build things better, to be safer, to fix long-standing problems that we have as a society. I think we need more intelligence for that. And I think the power of humans augmented by reasoning models, where you have basically a team that's helping you solve your most complex problems and helping you reason through the most thorny issues that you face. That's going to enable humanity to make some really important changes that help us all do better. So I'm really optimistic about where we're going.
I would say the optimistic vision for the future. I mean, I think this is very powerful technology, and the optimistic picture for the future is that it's going to increase productivity, it's going to increase scientific progress, and in the same way that we've seen incredible societal progress over the past 100 years, longer, obviously. Infant mortality has plummeted. A lot of great things have happened on many dimensions over recent human civilization. that's just going to accelerate. And all these great things are going to continue. And of course, there is the risk that with any powerful technology, there's both an upside and a downside. And I'm hopeful that the downside risks are also addressed. But I think I am I'm pretty optimistic that what we're going to see from these models is the ability to as you said, augment humans, to complement them, to enable scientific progress that would not have otherwise been possible or would have taken much longer to do. And that's, I think, a reason to be optimistic about where we're headed.
Thank you. That was wonderful. It's a great conference. Hopefully you can stay back for some questions. For now, we are at 0. Thanks, everyone.